I was asked to give a workshop, little mini workshop for the American Psychological Association last spring. And Alex was hassling me during that workshop about my hatred of R, which has not changed. But a lot of this slide deck is from there. So I've edited it, of course, because I can't ever leave well enough alone. But that will sound familiar. So I have actually two examples that go with this unit. One that's embedded in the slides that I'd already made for that purpose, and I threw a lot of syntax in there as well. And then I have a whole separate example that I made from scratch, so you'll have two examples for this concept. But what we're talking about is from empty models, so to speak, to adding level 2 predictors. And we're in general models, meaning we're predicting outcomes whose residuals are supposed to be normal at each level, in 2 levels in which the sampling dimensions are nested. So people nested in clusters is what we're talking about here. That's a lot of words, but I had to be specific, because as we grow throughout the semester, there's differences in each of this aspect of this. All right, so here's a model. The 2 sides of a general linear model, like this part right here, that's your model for the means. So trying to introduce some notation. In single level regression land, I have P for person here, since I know where I'm headed with this. Y is a variable, beta 0 is a constant, beta 1 is a constant, beta 2 is a constant. These are variables. So the lack of P subscripts on the betas here is important. What that means is that those betas apply to everyone's score equally. They are constants. I can have as many predictors as I want to up until n-1. So the model for the means is a weighted linear combination of how people's values on x1 and x2 translate into differences in y. These estimated constants are called fixed effects. The term fixed means every unit gets the same. Effects is a general term for which intercepts and slopes are more specific. So you'll see me say effects a lot, but I mean sort of both of these things most of the time. The model for the variance then, this thing right here, RE. It's usually written like this in stats books. So E is supposed to be normally distributed with a mean of 0 and some estimated variance. This is one number. So the use of a normal distribution in turn means that we have to assume constant variance because the normal distribution only has one variance in it as a parameter. If we said that E was something else, like E was maybe a Poisson variable, in that distribution, the variance changes along with the mean. So normality and constant variance go together based on the choice of the distribution for your residual. That's the basis of generalized modeling, to swap that out for something that matches better than normal for outcomes that are not actually continuous. Independent is the key thing here that makes this model unsuitable for clustered data. This model says everybody's E's are uncorrelated, and that's not likely to be true to the extent that people have these groups that they're part of. So E is one pile of variance, one variance component, because there's only one dimension of sampling across people, and that's it. That means that when we have more than one dimension, we got to add something else to build that in. Showing this graphically, here's an empty model. More specifically, an empty means model with respect to the predictors here. If I know nothing else about a person, what's my best guess for their outcome? Yeah, the grand mean. So that's what beta 0 becomes in this model. So in this distribution, here's where the mean is. If I wanted to predict the outcome for this person all the way down here, I could do that. The mean is not a very good guess for this person, so there's a very large negative residual because they're much lower than predicted. So to introduce the terms then into this, beta 0 is the model for the means. And that's where the term comes from, because at this point, literally the model says everybody gets the same mean. But as we add predictors, then it's a conditional mean based on your predictor values. So everybody with the same predictors would have the same predicted outcome, otherwise known as y hat in notation sense. And then the variance at this point is your outcome for each person minus what the model for the mean says it's going to be, which is just the mean. So in this case, this is literally just variance of y. So the job of this model is to spit back 2 descriptive statistics for y, the mean and the variance, the n. as you add more predictors in here, what should happen to this residual variance? Sigma squared sub e. As we add predictors, should it go up, down, or stay the same?
Down.
Should go down, right? Right? Yes, yes. Core concepts here. So what if I had a clustered sample instead? So embedded within this general histogram, I've got 3 clusters. Got a green cluster, yellow, and purple with 5 people each. That means at a minimum I need to change my notation. So rather than y sub p per person, it's PC for person and cluster. So last year, or 2 years ago, nope, yeah, it was 2 years ago and 4 years ago, I did PG for persons and groups. I'm switching it up for clusters this time. It's up to you what letters you pick. Every textbook on the planet does IJ. That drives me insane. J does not stand for group. That's G. You are allowed to pick your own letters to help people follow your notation. They do not have to be IJ or IJK. So same idea here. If we don't know anything else about a person, our best guess for their outcome is still the mean. However, in clustered data, we can make a better best guess by paying attention to which cluster they're from and incorporating that information into our naive starting point. And the idea of taking into consideration each cluster's mean forms the basis of what is known as a random intercept. So fixed intercept, everybody gets the same. Random, every cluster gets their own. So the new empty model, empty means random intercept model, to be specific, looks like this, where I still have my fixed intercept beta 0. I've added a new letter. Welcome to your new friend U. U has a 0 subscript because it's an intercept. U has a C subscript because each cluster gets their own version of U. What U represents is the difference between the grand mean and each cluster's individual mean. So that means that beta 0 here is now the mean of the cluster means. That's not going to be the same thing as the grand mean to the extent that clusters have different numbers of people across them. So we're breaking up the total variability in Y into pieces here. We have the mean of the cluster means. U then is how far off your cluster's mean is from that grand mean of the cluster means. So the green people, is their U going to be positive or negative? Positive. Yellow-orange cluster? Negative, and purple, negative. Yeah. U has a mean of 0 by definition because the mean of U is over here as the fixed part. So it's like fixed plus random puts it all back together again. So then beta 0 plus U0 gets to these dashed lines for each cluster. From there, E is what's left. So then E is the difference between the cluster's mean, which is given by the fixed plus the random intercept, to where each individual outcome is. So this is the first model that you will always estimate when you have clustered data. It tells you how much of the information is due to each dimension of sampling. How much of it is because some clusters are different than others, and how much of it is because of some people are different than others. We have not explained anything, though. All we've done is split it up. Take the total variability and allocate it to 2 different piles. Piles of variance. My textbook's website, not a coincidence. It's my stick for talking about these things. So in terms of notation, I'm following what is conventional in this field, where the variance of the U's across clusters is tau squared. I always write it with the subscript, meaning what is it the variance of, because there's going to be a lot of them to keep track of, whereas the variance of the people is sigma squared. Here is that same idea using multi-level modeling notation. So empty models still, no predictors, but contrasting what it would look like for an empty model for just a simple random sample of no clustering versus a multi-level sample. I'm using color here deliberately. Things in red are fixed effects that go into the model for the means. Things in blue are related to the model for the variance. So first switch here, we had beta 0 in the GLM model, picks up a C subscript here. That's because beta 0 is no longer a constant, it's a variable. Beta 0 is defined as the fixed intercept. This thing right here that looks like a Y or a V, that's gamma. Here's our friend U, which is the random intercept. Put them back together again in the level 1 model and pick up E, and you get back to Y. So the fixed intercept, the mean of the cluster means. Random intercept, how far off your cluster mean is from that fixed effect. E is what's left, is the level 1 residual, how far off you are from your cluster's mean. Putting it all together, it looks like this. So this is known as a composite equation because it shoves everything all in one line. Beta 0 is a placeholder that is often used in very complex multi-level models to help us keep track of what all is in it in terms of fixed versus random effects. You can write it either way. At the end of the day, this model only has 3 parameters in it, though. I have 1 fixed intercept. I have, oh, typo, let's see who can find it. I have 1 residual variance, and I have 1 random intercept variance.
TI.
Yep, do you know why? Because these
Fine.
slides came from the other class. And I am going to fix it right now. Best advice I was ever given, fix your typos right away. That way 2 years from now, you're not staring at them again. There we go, that looks better. So, 3 parameters. Now, I'm making a point of saying that because it does not matter how many people you have and how many clusters you have. The model does not estimate a separate U per cluster. U is the idea of differences across clusters that is actually the model parameter. The variance is what we're after. We don't need the U's. You can ask for the computer to spit them out, but they're actually not necessarily great estimates, and we wouldn't necessarily want to use them. We want to do everything simultaneously within a model and avoid having to output stuff and treat it as variables in a separate analysis. E, same way. The fact that there's only 1 E means that we're assuming that all clusters are equally variable. All clusters have the same amount of person-to-person differences within their cluster. That's an empirical question, but it's a starting point for these models. Okay, how are we doing with notation? That's correct. So this is...
What was that word, or the sentence that you just said? It's assuming that...
It's assuming, so the fact that there's only 1 E variance here is assuming that it's constant across all the clusters, which may or may not be true. So you can think of this as like the average variance of people from the same cluster. Some clusters might be more homogeneous than other clusters, but that's not in the model yet. That won't be in the model for quite a while, but it could be.
Is that?
Yeah.
Do you mean that, so in our R matrix, we have just the variance and covariance are 0, the independent structure, right?
Yes, yes.
Okay.
So for those of you who are familiar with the terms R matrix or G matrix for level 1 and level 2, this is a diagonal R matrix where you've got your variances on the diagonal, they're all the same, zeros everywhere else. This model says that the only reason why people from the same cluster are correlated is because of cluster mean differences, which is represented by my U, and that's it. So after controlling for which cluster you're from and allowing a mean difference as a function of being from that cluster, people are conditionally independent. That's what we're saying. Conditional on the U. So then a logical question that follows is, well, I've got these 2 piles. How big are they relative to each other? Next thing you would want to do, compute an interclass correlation. This goes in your methods section or at the beginning of your results, usually. There are many kinds of interclass correlations in the literature. This is known as ICC1 more formally, but when you say ICC, this is what most people will think of. I apologize to the measurement class. This is not item characteristic curve. This is different ICC. So it is the random intercept variance, which gives you differences between clusters. divided by that plus the residual variance, which is differences within clusters. So you can think of it as U0 variance is why don't all the clusters have the same mean? I don't know, because of cluster characteristics forthcoming. And then E variance is why do people from the same cluster still differ from each other? Remaining individual differences holding their context constant. So this ratio tells us how much of our variability is due to clusters. You can think of it that way most directly. So of the total variability, how much of it is because of cluster mean differences? Or you can think of it as the average correlation of people from the same cluster. When computed this way, intraclass correlation ranges between 0 and 1. 0 would be no cluster effect. People from the same cluster have nothing to do with each other. 1 would be it's all clusters, everyone from the same cluster looks exactly the same. As long as you are somewhere in between 0 and 1, you've got variance of each kind, you're good to go with your multi-level analysis. Another way to think about this is as an effect size for how much of your outcome dependency you have due to cluster differences. How big is your dependency problem or opportunity, depending on how you want to talk about it. So it's constant cluster dependency is what's being captured here, treating people as exchangeable. And I will die on this hill that it is not appropriate yet to talk about explained variance. People will disagree with me, but I'll tell you why. Because we know that clusters differ from each other, we don't know why. All we've done is take an error and split it up into two piles. So if I have an ICC of 0.8, what does that tell me? Counting? ICC of 0.8 tells me what? Let's see, let's go to Jacinta for a second.
80% of the variance has to do with being in different clusters.
Yeah, most of the action is cluster differences. Yep, most variance between clusters. What if I did the other 1.2?
So then fewer folks within the cluster would be similar, or the cluster would have less of an influence.
Cluster has less of an influence. People are less similar to each other. You can think of it that way. That's where you're going. Yep. In clustered data, ICCs tend to be kind of small. I think the highest ICC I've ever seen in real data is like 0.3 in a clustered design. Whereas in longitudinal data or other types of repeated sampling, you can go up to ICC of 0.8, 0.9 real easily. It just depends. So I've had folks in the past be confused as to how this correlation represents within cluster correlation, but the numerator is between. So I just have a little slide on that. So this is the picture that would be consistent with a large intraclass correlation, where I have large differences between the cluster means and relatively small differences around the cluster means. That would translate into a relatively large intraclass correlation. And if you think about it in the correlation equals prediction point of view, then if I know the score for one purple person, I can do a pretty good job guessing what the score for another purple person would be if there's a really strong correlation, right? They're going to match. Whereas if I had something like this, now the differences between clusters are quite small relative to the differences within. If I know what this purple person's score is, I basically random guess as to what another purple person's score is, right? They're all over the place. So that translates into more within variance and a much smaller correlation, much less predictability of how someone from the same cluster would do if you know one person's score. Yeah.
What would be, say, our cutoffs for like small or large ICC numbers?
I think it's all contextual.
Okay.
So like an ICC of 0.3 in a classroom setting would be huge. An ICC of 0.3 in a longitudinal setting would be very small. Okay. As long as you're somewhere between the two, right? So if it were 1, that means you don't have any people variation. All you're doing is predicting cluster differences. You may as well just aggregate to the cluster level and do a single level regression at that point. Like you're not going to get that much more out of it because all the information is at level 2. The corollary to that then, I think, is coming up soon. What if you have an ICC of 0? Could that happen? That might be one way to check to see if your random assignment worked, right? If people are randomly assigned to clusters, there should be no correlation of people from the same cluster. There should be no interclass correlation. There should be no between cluster random intercept variance. I caught myself just in time. So here's an example. As I told you, this is from the little mini workshop I gave, so I just threw all the programs into one slide. I put up a link to where the original files for this are, if you'd like to go play with them. So here's what an empty model would look like in SAS, in R using Elmer, in Stata using mixed, or in SPSS using mixed as well. I'm going to have a separate example where I walk you through the packages I'm emphasizing, so don't worry about understanding all of that. I'm going to borrow a data set from the Snyders and Bosker textbook that is supposed to be real data, but I have my doubts. We're predicting language outcomes for 3,500 and some odd students from 191 schools. So my empty model would look like this. Here's the output from SAS mixed if I forget the U. So if I estimate a single level model where all the variance is in one pile, I get an intercept that's a fixed intercept of 41.46. The mean is 41.46, not a coincidence. Likewise, the variance across all people, regardless of what cluster they're from, is estimated as 77 and some change. That's what it was in the data set, not a coincidence. This, I'll explain why, but we're never going to look at these p-values right here. You can't look at these p-values for Wald test for variances because they can't go negative. If I add in the random intercept, what it's doing is taking my total variance and it's splitting it into 2 piles. They don't add to be exactly 77 because these data sets are unbalanced in size, but it's pretty close. So there's a couple differences in the output that are relevant. First is that the fixed intercept has changed a little bit. That's because it means something slightly different. It's the mean of the cluster means. So to the extent that clusters have different numbers of people, that may change as a function of weighting versus unweighted. Check out the standard error of the mean. Much bigger. Because this is now a cluster characteristic, and there are only 191 clusters. So the standard error appropriately understands the sample size that goes into this standard error of the mean. Degrees of freedom for this also change quite a bit. We're using a method called Satterthwaite. Talk about that in a little bit, probably next time, not a little bit, to do that, but it's closer to the number of schools in this example. Then we get 2 variance components. 17.8 is the random intercept variance. The remaining residual variance is 62. I can plug those into my interclass correlation formula, and it works out to be 0.22. Yes?
So in the example that you were talking about where they had the 5 and 5 treatment control, what would it be the standard error that you were looking at of like this is just way off, or like it's the sample size is way too small, and therefore, I guess like in this example, if the sample size was 10 schools instead of 191, how might the results change?
So the question was, if we only had, say, 10 schools rather than 191, this standard error would be much bigger.
Right.
Because we would expect a lot more inconsistency across repeated samples as to what that mean would be, because a mean of 10 things is wiggly relative to a mean of 191 things. And the degrees of freedom would be something closer to 9.
Got it.
So, yes, thanks for the question. So 22% of the variability in language has to do with what school you go to. On average, some schools have better language outcomes than other schools. That's what this means. Now, another thing that may be useful to compute based on the information from an empty means model, this is much more useful in the context of sample size planning. This isn't something that I would typically see reported in a results section, but it's useful for people who are anticipating how many people they need. It's called a design effect. The technical term here is the ratio of the variance using a given sampling design to the variance using a simple random sample from the same population, given the total sample size is the same either way. To put it more directly, perhaps a little crudely, but I feel like this is the most direct way to say it, the design effect tells you how screwed you are because you have a clustered sample. That's what it means. It's how many more people do you have to recruit so that you can have as much information as you would have from an independent, unclustered sample. It relies on two pieces of information. One is the interclass correlation that we just saw. The other is the number of people per cluster, so level 1 sample size. That plus 1 is the design effect. So that means at a minimum, the design effect is 1, and you have as much information as you have people. The denominator would become 1, then your effective sample size is your actual sample size. As interclass correlation goes up, and as you get more people per cluster, the higher your design effect is going to be. That means the less information you actually have. Here's a couple examples. Let's say that I have a hospital setting where I have 5 patients each from 100 doctors with a relatively strong interclass correlation of 0.3. Plug those things into the formula, my design effect is 2.2. That means that even though I actually have 500 patients, in terms of the amount of unique information they provide, I only have 227. So I need to recruit 2.2 times as the sample size if it's clustered than if it were not clustered. What if I have a really small interclass correlation, like 0.05? Like, that's barely anything, right? Can I just pretend that I don't have a clustered sample? Sadly, no. In this case, if we have 20 students from 50 schools, that's still a design effect of about 2. Cut your sample in half. In the example that we have here, using our numbers, on average, we have 19 students per school. That's just the arithmetic average. There's probably other ways you could try to index that, but just using that for simplicity. My design effect is 5. So that means that even though I have 66 students, I actually only have 712 when it comes to the information they provide. I know.
So if you're in this limited setting though, you only have this amount of stuff, like maybe you only have so many doctors, providers, students, whatever, like how, maybe this is like the next part on the next episode or whatever, but like, how do we get this ICC down then? Or I'm sorry, the design effect. How do we get the design effect down?
How do we get the design effect down? We get each of the ingredients down.
Okay.
So you need to lower the interclass correlation and or lower the number of people per cluster. So like from an ideal sampling perspective, 1 person per cluster.
Okay.
And you're like, what? No,
And
but
that
it sounds,
bizarre, right?
yep, like no one would do that, but like that's the most efficiency. Because then you're down to no clustering because it's 1 person per cluster. You can't separate out what's a person thing from a cluster thing. So that's bad for reasons, but like mathematically, that's optimal. Otherwise, get your ICC to 0. This part goes away, and you're left with no penalty for having a clustered sample. Now, how do I get the ICC down? Well, my ICC is 0.22. I need to reduce this 17 into a smaller number. I need cluster characteristics as predictors, because if I can explain why some of the clusters have higher means with things I know about the clusters, there's less correlation remaining in the residuals, there's less dependency, there's less design effect.
Can you say that one more time?
So the way that I can help solve this problem is trying to find measurable cluster characteristics that go into my model as a predictor to try to get this 17 that's driving this into a smaller number. If I can explain why some clusters have a higher mean, then the residuals that are left over have less dependency, less correlation, less design effect. So in practice, like if I'm writing a power analysis section, I would ask whomever's asking me to write this, what's a reasonable ICC for this type of research design? Go to previous literature, give me a range, right? Maybe it's 0.1 to 0.3, something like that. And I would get out my calculator or my Excel spreadsheet and figure out like what the reasonable range of design effects would be if those were my inter-class correlations. So most people have a fixed level 1 sample size because it's just whatever you have, right? Like this doctor only sees this many patients, or this school only has this many kids.
Right.
Like that part you can't really fix. And if you're already in the school and it's not any more work to get all the kids to participate, then why wouldn't you do that? Yes?
What if it's different how many students you have in each school?
Then different ways of putting this part would probably yield slightly different answers. And you might want to do a range type of thing. So like if the minimum size is this, like best case, worst case for in terms of level 1 sample size and for ICC, and come up with sort of a range of design effects.
Using like the minimum and the maximum.
Something like that. There's probably other things on it. You can look in, Snyder's and Bosker have a little bit of discussion on this, and I'm sure since this is, 11 years old, there's other things too, but these are just sort of anticipation types of techniques. Back in the day, people used to compute design effects and then manually multiply their standard errors by them to like fix the clustering, but we don't do that anymore because we have the technology. That'd be like the Atari version, and we're at Nintendo Switch level. To give you a thing here. All right, 144. I'm going to save my soapbox for next week. That's all right with you, because that's more than a minute. I have a big soapbox I have to stand on. I'm a short person. All right, any questions before we wrap things up for the week? Because it's not garbage day.
It's garbage day in Oxford.
It's garbage. Oh, see, that would totally mess me up.
Every time you
Garbage
say
day
it.
in Tiffin.
Okay,
Garbage days are.
I know. That's the nature of garbage day. Everyone has a different one, but my garbage day anchors my week, and it's not garbage day, which means I say, have a good weekend. Let me know if you need anything. Do your first formative assessment and homework 0 if you can, please, by Monday. All right? All right. Thanks for being here, folks. Thank you, Zoomers. See you on the other side.